Let's start our conversation with magnetic field and magnetic force. Once again, when we start a new topic, we always try to understand the topic with something we already understand, and that is the gravitational field, gravitational force, electric field, electric force. So, when we talk about the gravitational force and gravitational field, let's start with gravitational field. Okay, so this is the field, gravitational field, and this is the electric field. Gravitational field on the mass, let's say Earth. Electric field on a positive monopole. Electric field with negative monopole. Electric field on a dipole. This is magnetic field, B for magnetic field. Magnetic field on a north monopole. Magnetic field on south monopole. Magnetic field on a dipole. Electric field on two like charges. Magnetic field on two like poles. Okay, so the field, gravitational field on a mass is inward, all direction. Okay, so the field is uniform, right? Which is G is equal to 9.8 Newton over kilogram. And the equation is G is equal to 1 over R squared, which allow you to do the graph. Well, the graph, if you want to start the center of the Earth, so this is the Earth, this is the Earth center. At Earth center, the gravitational field is 0, and over here on the surface is 9.8. We're going to use 10. Why it is 0 over here? Because so right here, if you are right over here, right, this is the field. If you're right over here, this is the field. If you're right over here, right, this is the field. If you're right over here, this is the field, right? You're looking for anything, baby? Yes, I do. I can share my chalk with you. Yeah. Okay. However, if you are in the center of the Earth, your field is actually 0. Why is that? Okay, so you are here in the center of the Earth. So there is a pole. The other pole was downward, but this pole is upward. This pole is this way. This pole is this way, and this pole is this way. So what does that mean? This one cancel with this one. This one cancel with this one. So the field size is 0 in the center. On the surface, this is 10. Okay, so from center to the surface is increases linearly. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It increases linearly like that. And then once you are on the surface, this is surface, and then it decreases. The field decreases. This is field. Field decreases as the distance increases. Okay. So what is the another equation? The equations for the field is Fg over m. Another equation for the field is big G big M over R squared. So these all three equations are equally good. This equation is especially good to graph. And the other two equations are going to help you find the size. So for example, you want to find the field over here. So over here, the field is how much? 10. If you want to place yourself 1r above the surface, what would be the field over here? Your field would be 1 over r squared, which would be what? 10 over r squared, which would be 10 over 4, which would be 2.5. So your field would be here 2.5 Newton over kilogram. Your field over here would be 10 Newton over kilogram. Your field over here is 0. Okay, so you get the point. Very nice. Okay, now positive monopole. So this is positive charge. Positive monopole goes outward, all direction. Okay, so again, the equations and equations would be same. So this would be E is equal to 1 over r squared. So the graph would look like exactly the same. This is E, this is distance. All right, as distance go up, field goes down. Okay, what does that mean? If you have a charge, okay, let's say, let's put positive charge over here, put a positive charge over here, right? It can create fields. Let's say this is 1 nanocoulomb. All right, at 1 meter from the charge, this is the main charge, and this is the test charge. Put the test charge over here. Okay, test charge does not create the field, the main charge does. So then what is the field over here? The field over here is 9 Newton over Coulomb. If you put the test charge over here, what is the field over there? Which is 2 meter. The field over there is 9 divided by 4 Newton over Coulomb. Okay, so that's by using the formula E is equal to Fe over small q, or E is equal to K big Q over R square. Now, if you consider this one, let's consider this. If you have, say this one is, if this one is, for example, 2, field is 2 Newton over Coulomb, then what is this one? 1, 2, 3, 4, 5, 6, 7, 8. This is going to be, field is 4 Newton over Coulomb. Why is that? Because this is double as strong, because this has twice as many field. So the field strength depends on the field lines. If you have twice the field lines, the field strength is twice as strong. You have put a negative charge over here, so what would be the field lines? Negative would be inward, 1, 2, 3, 4. So the field, the size of the, let's say, size of the field is negative 2 Newton over Coulomb. So this one should be then 1, 2, 3, 4, 5, 6, 7, 8. So this one would be, field is negative 4 Newton over Coulomb. Don't forget the negative sign over here. And the equations would be E is equal to, same thing, 1 over R squared, or E is equal to Fe over Q, or E is equal to K big Q over R squared. Okay, now dipole, what does that mean? If you have positive over here, you have negative over here. The field goes from, this is source, and this is sink. The field starts at positive, goes to the negative. Okay, so how do we draw this one? 2 Coulomb negative 4 coulomb. Okay, so let's say you have 1, you have 2, so you have altogether 3, and you have 4. Then this one would be 5, 6, 7, 8, because this is the magnitude is twice as great. Okay, north monopole. Okay, so north monopole, you can draw it, but it doesn't exist. South monopole, again, you can draw it, but it doesn't exist. It does not exist. Yeah, dipole. So magnetic dipole is just a magnetic, it's a bar magnet. So you have north and you have south. North behave like positive and south behave like negative. So again, north is a source and south is a sink. Okay, two like charges. Okay, we can put two like charges. You have a positive and you have a positive, and they repel each other. If you need to draw the field line over here, the field line gonna be just like this. If you want to draw field lines over here, field line is gonna be like this. Why is that? It's because let's say this is A, this is B. The A gonna look like this, B gonna look like this. So if this one is A, then what is this one? AX. This is AY. And if this one is B, this is BX. This is BY. AX, BX cancel. AY plus BY is just a Y. Okay, great. Two like pole, just like that. You cannot separate two like poles, so you have to use a bar magnet and put two north pole close to each other, like placing two bar magnet with two like pole facing each other. It's going to be like that, positive and positive. You won't be able to touch them because there will be repulsive force. All right, so now the magnetic field, we're going to be talking about magnetic field today and magnetic force. Okay, so when we talk about magnetic field, let's start our conversation with magnetic field. So you're going to use the right hand rule to understand the magnetic field, and we're going to use the right hand rule to understand the magnetic force. Okay. All right, so the magnetic field. The gravitational field, electric field, gravitational field is G, electric field is E, magnetic field is B. Gravitational field discovered by Sir Isaac Newton, 1665. Electric field discovered by Faraday, 1832. Faraday's law of induction, we're going to do it tomorrow. The same year, 1832. Magnetic field was Hans Ørsted, Danish, 1820. Same year current was invented by Ampere. Okay. All right. So our focus is going to be magnetic field. Oh, also magnetic field. Also, the magnetic field direction was conceptualized by Tesla. All right, 1882 or something. Gravitational field, you have the SI unit is Newton over kilogram. This one SI unit is Newton over coulomb. This one SI unit is Tesla. Okay. So let's start our conversation with magnetic field. So one day, 1820, Hans Ørsted was trying to demonstrate. He was a physics teacher. He was trying to demonstrate how he can place the current in the wire. Okay, good. So how you can place the current in the wire? Okay, you can do many ways, but in 1820 universe, there was only one way you could put current in the wire, and that is you have a lemon can give you electrolyte. You use the copper or zinc, all right, and you use copper to create the two terminal. Zinc has the copper electrolyte is copper electronegativity is greater than the zinc electronegativity. So zinc will lose the electron. If zinc lose the electron, zinc will become positive, and copper gain the electron, copper will become negative. You put the wire between this positive and negative terminal. What happens? The voltage will kick the charges. Charges will carry the electron. Okay, so if charges start moving, what we call the moving charges current. So this is how you can put the current in the wire, and that's exactly how Ørsted put the current in the wire in 1820 universe in Denmark. Okay, so there was a wire. He placed the current in it, just the way I did. Okay, using the battery. Okay, created by two terminal, positive and negative. By accident, he had a compass next to the wire that carries the current. And every time he placed the current in the wire, he saw that the compass needle deflect 90 degrees. And that gave him, that was the discovery. That's really surprised him. That was the biggest discovery, 1820. And now, speaking of that, I just want to remind you how the compass behaved. See, this is the Earth. Earth has a North Pole and South Pole. And if you put a compass over here, see, and then compass needle would be like this. This is compass needle, and this is the red one. So it is kind of directed to the north. Now, a few minutes ago, you remember I showed you the North Pole repel. All right, they do not attract. So why the compass needle, the compass needle, which is this is compass needle, which is north because it's red. I don't have red color, so I'm using yellow. So it is pointing toward the north. It's because this is geographic north. The compass cannot read geographic north. This is geographic south. The compass is actually reading the magnetic south. So geographic north is magnetic south. Geographic north is equal to magnetic south. Okay. So yeah, so the north needle of the compass facing toward the South Pole. And that makes sense because if you have a magnet, bar magnet, that's what the magnet do. This is source, this is sink. Okay, this is source, this is sink. So they face each other, not looking for south. Good. Now, the earth itself is a bar magnet. Earth itself is a bar magnet. Okay. Now, you probably think why the earth itself is a bar magnet in the first place. It's because the structure of the earth. What about it? Earth has layers. You have the inner core. This is inner core. Okay, so I'm going to write this is 1, this is 2, this is 3, this is 4. So inner core. And this is outer core. This is outer core. This is what we're going to call mantle. And this is what we're going to call crust. Crust. This one is about 500. The maximum it can get 500 kilometer. This one, the maximum it can get 3,000 kilometer. The maximum this one get is 5,000 kilometer. And the maximum this one gets 6,000 kilometers. So how many kilometer you have? You have 8,000, 8,000, 6,000, 14,000. So our diameter is about 13,000. Okay, so that checks. Okay, so I said approximately. So there is a range, of course. Temperature in Celsius, this one can get as much as 200 Celsius. This one get 2,000 Celsius. This one get 5,000 Celsius. This one gets 6,000 Celsius. This one's pretty solid. This one is melt, liquid. Okay, what is liquid? Iron and nickel. So this one made of iron and nickel. This one made of rock. This one also made of rock. This one also made of iron and nickel. So the earth mostly made of iron and nickel. So now you know why the earth is a magnet in the first place. So we are trying to cover something called magnetic field. We're going to start our conversation with a wire, right? What about the wire? You have a wire that carries the current. The direction of the current is to the north, right? Now, right-hand rules tell us, you have to curl your finger around the wire that carries the current. So place your thumb at the direction of the wire, okay, and curl your finger. If I do that, then I have to enter. This is enter. This is exit. Okay, and it's counterclockwise. Hopefully you see it's counterclockwise because this is counterclockwise. As you see, my hand is rotating in a counterclockwise. So this is counterclockwise. Okay, good. So this is counterclockwise. So what is counterclockwise? The field is counterclockwise. What field? Magnetic field. Magnetic field is counterclockwise. And magnetic field is like a cross section of a cylinder, like a circle. Consider a circle. Circle made of point equidistance from the center. This point is L, this point is L2, this point is L3. So this L and this L you can say delta L. So you can say that from this one to this one is delta L. So then all the point is sum of what? All the point, which is the magnetic field, is equal to mu current. So how you can replace the delta L? Delta L is 2 pi r. Magnetic field is equal to mu times current. So this is called Ampere's law. Ampere's law. So what does Ampere's law tell us? Magnetic field is equal to mu current over 2 pi r. So mu is 4 pi times 10 raised to negative 7 Tesla meter over ampere. Okay, that's the mu. Okay, so now we're gonna quickly give you some examples, like 4 or 5 examples. Example number 1, there is a current 45 amps flowing through the wire. Find the magnetic field at location A, which is 2 centimeter from the wire. So find the magnetic field over here. Problem number 2, same thing. However, the current is moving different direction at the same magnitude. Current is 45 amps. You have to find the magnetic field at location A, which is again 2 centimeter from the wire. Number 3, we're gonna do it here. Now maybe here. Wire current is, let's say, 20 amps flowing through the wire to the north, and you have to find the magnetic field at location A, which is 2 centimeter above the wire that carries the current. Number 4, you have the wire which current carries to the east 30 amps. You have to find the magnetic field at 2 centimeter above the wire. And number 5, you have current which is 20 amps, and this current which is 30 amps. You're going to count 1 and 2, the distance between 1 to 5 centimeter. I want you to find the magnetic field over here, which is 2 centimeter above the wire 1. You can pause the video and use the right hand rule to find the answer for this 5 problem. The magnetic field for this one is mu current over 2 pi r. So mu is 4 pi times 10 raised to negative 7. Current is 45. You have 2 pi. You have 0.02. Okay, so you see pi cancel. 2 goes to 4 twice. 0.02 goes to 2 100 times. Right. So you have 4.5 times 10 raised to negative 4. 4.5 times 10 raised to negative 4 Tesla. Now, as my thumb is the direction of the current and my finger calls, so this is into the pace or counterclockwise. This is exactly going to be the same, 4.5 times 10 raised to negative 4 Tesla, but outside the pace or clockwise. This is, we're going to see, this is the direction of the current. So this is enter, this is exit. So this is clockwise or counterclockwise. So this is, so this is, let's see, this is, let's see, look at my finger. This is clockwise, this is clockwise, so clockwise. Hopefully that looks like clockwise to you. So the current at this location is V is equal to mu 2 pi, mu current 2 pi r. So mu is 4 pi times 10 raised to negative 7. Current is 20. 2 pi, r is 0.02. 2 goes to 2, 2 goes to 200 times. So you have 2 times 10 raised to negative 4. 2 times 10 raised to negative 4 Tesla. And this one out of the pace or clockwise. And you see whenever it out of the pace is clockwise. When it's inside the pace is counterclockwise. That's another thing you should have discovered by now. The magnitude would be the same, which is 2 times 10 raised to negative 4 Tesla. However, this one would be, let's see, counterclockwise. Why is that? Because this is cross, this is dot. So this is, of course, cross. And whenever it is cross, it is counterclockwise. Hopefully this is convincing, look like counterclockwise to you. So this is called counterclockwise. Hopefully my hand look like counterclockwise to you. Okay. Now this one is going to be, this is equal to positive, this is equal to negative. So you want to find the field over here. So the field over here is mu current 1 over 2 pi r1 minus mu current 2 over 2 pi r2. So you're going to factor out mu 2 pi, right? Current 1 r1 minus current 2 r2. So you're going to write mu, which is 4 pi times 10 raised to negative 7, 2 pi. Current 1 is 20, this is 0.02. Current 2 is 30, this is 0.07. Why is that? 5 times 5, 5 plus 2 is 7. So this is 2. So B is 2 times 10 raised to negative 7. Hopefully you see it over here. And this is 1000 minus this is 430. So let's do it over here. So 2 times 10 raised to minus 7. 1000 minus about 400, which is 600. So 600 times 2, 1200. I'll just write 1000 times 10 raised to minus 7. This is 1.1 times 10 raised to minus 4 Tesla. The direction is over here is again outward. Okay, good. This is the magnetic field. When we do the magnetic field, we call our finger. Now we're going to do magnetic force. When we do magnetic force, instead of calling our finger, we read our palm. Baby, you ready? Okay. So we're going to read our palm. Huh? Oh. Okay, so try. Okay, so for the force, we're going to read our palm. What do I mean? Let's see, this is what I mean. Consider a current which is, let's say, 2 magnitude less than the speed of light to the north. And consider a field which is like 5 Tesla. On what? Positive charge. What is the direction of the force? Well, it's very easy. My thumb is at the direction of the current and my fingers is at the direction of the field. You're going to read my palm. It's outward. So the force is outward. Now find the size. So force is QBV sine theta. What is the angle? The angle between the field and the velocity is 90 degrees. So F is QBV. So F is 1.6 times 10 raised to negative 19. B is 5. V is 2 times 10 raised to 6. Okay, so F is 1.6 times 10 raised to negative 12 Newton outward. Okay, another example. Maybe I'll give you just one example that's gonna give you all the direction for the force. So I'm gonna give you just one example instead of giving you many examples, just one example, and that's gonna give you full understanding. So this is a proton. Let's say the velocity is v, right? And at this, okay, so velocity is v is equal to 3 times 10 raised to 6, which is 4 magnitude bigger than the speed of sound. 2 magnitude is smaller than the speed of light. Okay, so the velocity of this proton is to the right or to the east. Now, the field is at this location, the field is inside. So the field is like this, uniform. Especially on the loop, the field is uniform on the loop. So if you have a loop, the field is uniform on the loop. Okay. So field is 0.1 Tesla at right here. Okay. Now, if you use your right hand rule, what would be the direction of the field, direction of the force? So this is, my thumb is at the direction of the velocity of the current. Good. Now my finger is at the direction of the field. So you read my palm, which is north. So this is your force. What type of force? Centripetal force. Now, let's use this analogy to understand what's going on. This is Earth. This is Moon. If you remove the Earth, Moon gonna move with a constant velocity in a straight line. Since you cannot remove Earth, Moon will move around the Earth. At some location, Moon is gonna be here. At some location, Moon gonna be here. At some time, Moon gonna be here. At some other time, Moon gonna be here. It's not gonna move in a straight line because there is something called centripetal force. This tells us that Moon belongs to me. If you translate Moon belongs to me, that's what this arrow means. So what is the source of this centripetal force? Gravity. Okay, so what is the source of this centripetal force? Magnetic field, magnetic force. Okay, so then would this proton be able to keep moving in a straight line forever? No. Why? Because there is a centripetal force which is to the north, 90-degree angle. Not possible to move in a straight line, although it wants to because Newton's first law, but it can because there is a net force which is 90-degree. Okay, so then there must be a time t when its velocity is exactly 90 degrees shifted. There would be at least one time, because if this is the Earth, Moon gonna be here, and then Moon gonna be here, and then Moon gonna be here, and then Moon gonna be here. There is no choice. So Moon velocity vector would change as 90 degrees. There would be a time, exactly time when the Moon is gonna be here, exactly time when the Moon gonna be here. If this is the Earth, there is no choice. Okay, so there would be a time t when the proton gonna be here and the velocity vector exactly look like this. And since the field is the same, uniform, right, at every location, especially in the loop, then how are you gonna find the force vector? Okay, velocity, this is thumb is at the direction of the velocity and my fingers is at the direction of the board. So you read my palm. If you read my palm, this to the west. Okay, there would be exactly time t when the velocity vector is 90 degrees shifted. There would be a time t when this proton has no option but the velocity vector is 90 degrees shifted. And since the field on the loop is uniform, which is equidistant from the center, then the field would be what? My thumb is at the direction of the velocity and the finger is inside the board. So you read the force is my palm is to the south. There must be a time t when the velocity is exactly 90 degrees shifted than the previous one, no matter what. No matter what. Okay, so if that is the case, and then the field doesn't change, the direction of the field is same. Okay. Now, this is my thumb is at the direction of the current, and my finger is inside the board, so you read my palm, which is to the east. All right. So what do you see counterclockwise? What is counterclockwise? Field created by what? The proton. Now, can you find the radius of this loop created by this proton? Of course, you can. Okay. In this loop, the field is uniform, meaning that the size of the field is 0.1 Tesla. Yeah, you can find the radius by Fc is equal to Fb. Fc is equal to Fb, right? So Fc is mb square over r is equal to q b v sine theta. Okay? Sine theta, every single point, the velocity vector and the field, velocity and the field is 90 degree. So mv square over r is equal to qbv. V square and v, so just one v remains. So what do you have? You have mv over r and you have qv. So then r is mb over qv. Okay. So what is m? M is 1.67 times 10 raised to negative 27. That's the mass of proton. V is 3 times 10 raised to 6. Q is 1.6 times 10 raised to negative 19. B is 0.1 Tesla. And this is what? R. Don't forget. 1.6, 1.67, almost same. 0.1 goes to 3 30 times. So you have R is equal to 30 times 10 raised to negative 27 positive 25 meter. So R is equal to 0.3 meters. So this loop is 0.3 meters. On this loop, the magnetic field is uniform, which is 0.1 Tesla. Okay. If you don't understand anything we did, what did you do? We did many things. We did a right-hand rule for magnetic field and right-hand rule for magnetic force, among the other things. If you did not understand anything, write your questions in the comment box below.